Hi, we're going to finish up our discussion of thermodynamics. So that will be focus 5, where we take everything we've learned about thermo and apply it to chemical equilibrium. And then the other two things we'll do this week, we'll do a chapter on statistical mechanics, which links quantum mechanics to thermodynamics. And then our very last chapter will just be experimental kinetics, very similar to what you did in 108, except we'll do the calculus. Okay, focus 5. Chemical change. So the guiding principle is that the spontaneous direction of a reaction at constant temperature and pressure is in the direction of decreasing Gibbs energy. From what you already know, that's equivalent to saying that's it goes in the direction of increasing total entropy of the universe. Because when we're at constant temperature and pressure, we have that relationship between delta S total and delta G, where they're the negative of each other. So we're going to do topic A, B, and C. We're going to skip D, E, F, and G, only because they're types of equilibrium you put a lot of time into in other classes, like acid-base equilibrium, mostly. Yeah, those are the ones that those are covering. And then we'll come back and we'll apply what we know about equilibrium to ions in solutions and therefore electrochemical cells. And you've already seen some on electrochemical cells, but it's always at the end of 108, so I feel like it's always something good to go over again because you're tired at that point and probably don't remember as much. So topic 5A, the thermodynamics of a reaction. So the key idea is that at constant temperature and pressure, a reaction mixture tends to adjust its composition until its Gibbs energy is a minimum. So sometimes that happens, you have Gibbs free energy versus composition when you have mostly pure reactants. And then you'd have a small equilibrium constant, mostly products, you'd have a large one. And sometimes where the composition is about 50-50, and then your equilibrium constant would be about 1, depending on the stoichiometry. So at constant temperature and pressure, get it at home, pretty much have to follow along in your book. At constant temperature and pressure, a reaction mixture tends to adjust its composition until its Gibbs energy is a minimum. Exactly what the key idea is, we'll just start right out with that. So one of the objectives of this topic is to show how to use thermodynamic data to predict the equilibrium composition and to show that composition depends on the conditions. So first, when we think about the reaction Gibbs energy, we remember that when we draw these double harpoons, they call them here, that it denotes a situation where we're at dynamic equilibrium, where there's no net change, even though things are reacting forward and backwards. And so the reactions that they go through are first just this one that has stoichiometry of 1 to 1, and then on to more complex stoichiometry, where you're making ammonia from 3 moles to 2 moles, and then just generalizing that to what we're going to talk about is generalizable to any reaction where you have A and B at some stoichiometric amounts, going to C and D at some stoichiometric amounts. So it has to be true that if in that first stoichiometry, so we have 1 to 1 right here, then the change in Gibbs energy is the chemical potential of the product times the number of moles of product that react, and then minus the chemical potential of reactant times the number of moles. And that minus comes in simply because if F goes up, G goes down, so they're related in a negative way. And so the change in Gibbs free energy for the reaction is really the difference in the chemical potential of the two compounds, the product and the reactant, times the number of moles that react. And so if you rearrange this equation, what you see is that the Gibbs free energy change for a reaction is also really equal to a derivative, because if you take the dN over to this side, you get dG dN, change in chemical potential, or change in Gibbs free energy if you change the number of moles of reactant or product, and that's just equal to the difference in the two chemical potentials. So just says here, which is an important concept, that it follows that there are two ways to interpret the Gibbs free energy change for a reaction. The first is that it's the difference of the chemical potentials of the products and reactants at the current composition. So remember, these two depend on composition, the chemical potentials. So at the current composition. And second, because delta G is a change in G divided by the change in composition, it's also the slope of the graph. And so when we get down here to where Gibbs free energy is a minimum, the slope of that line is also equal to 0. My cat wants out. You can go out, Keeks. Come on, hurry up. Keep going, girl. So this just goes on and looks at the more complex ammonia reaction, and you'll see that it's always going to be exactly the same situation. You'll have more chemical potentials and their stoichiometric coefficients, but the concept is the same. So delta G of a chemical reaction equals 0 when you're at equilibrium if the process is taking place at constant temperature and pressure. And so we can show that as composition changes, the Gibbs free energy changes. So we will see where this equation comes from. You use this in Chem 108, but now we'll know where it comes from all of our work through Focus 4. So this Q in here, you remember, is an expression like an equilibrium constant, except it's at any random concentrations. So we will see down here where that Q comes from exactly. So I'm going to go through that justification on my own sheet of paper, because when you're going through a derivation, I think it's hard for you to follow me with that little text. So in order to get to that equation that we used in Chem 108, this one at the bottom, we go back to topic 4D, where we showed that the chemical potential changes with composition relative to some standard state. So chemical potential of J equals the chemical potential of J if it was at 1 bar pressure, plus RT ln of the activity of J. And the activity of J, if it's a gas, would just be the pressure of, I should say, pressure of J over the standard state pressure. So we derived that equation. That's just the relationship, or that's just the equation that started out with G equals V dP. And we integrated it for perfect gas to see that you end up with changes as a function of the natural log. So if we just look at a basic stoichiometry, one reactant, one product with different stoichiometric coefficients, then the change in Gibbs free energy for that reaction would be the number of moles of C times the chemical potential of C minus the number of moles of B times the chemical potential of B. So if you write each of these guys in terms of the top expression, so the chemical potential of C is going to be what it is at the standard state plus RT ln of activity minus the chemical potential of B in its standard state plus that same term, except now it's the activity of B and the stoichiometric coefficient of B. So if you group terms, you can group together the chemical potentials of C and B when they're in their standard state, and you get delta G for the reaction in its standard state, plus RT, because this is the difference in the chemical potentials equals a delta G, plus RT. And then if we group this, so if we pull out front the RT, then we're going to have C ln of AC, B ln of AB, the difference of those two. C times ln of AC is ln of AC to the C, so that's just a natural log relationship. And when we take the difference of natural logs, it's just the natural log of the ratio. So I'm going to do that for each of these, take B up here, and then when it's minus ln of AB to the B, that goes in the denominator. And so here's the equation that you used in 108 derived here so that you have a little better understanding of where it came from. Okay, so when a reaction reaches equilibrium, a couple of things are true. The first is that we replace Q with K. And so if we did a more general stoichiometry, you'd see that my two component system, one reactant and one product, can be generalized to any number of reactants and products, and the Q will have the same expression. The reactants will be in the denominator, the products in the numerator, each raised to their stoichiometric coefficient. So when we're at equilibrium, that Q is equal to K. The reaction forward equals the reaction backwards. And so also at equilibrium, delta G equals 0. So delta G equals the standard state Gibbs free energy change plus RT ln what would have been Q, but now if we're at equilibrium, that's K. And so when you rearrange this expression, you end up seeing that you can measure an equilibrium constant by measuring the standard state Gibbs free energy for that reaction, which is actually pretty profound. So stop and do self-test 5A.2 on page 181, where you just use that equation. And I don't think there'll be any surprises. So you want to make sure you think that when you ask if a reaction is spontaneous, you always have to ask, is it spontaneous at the conditions I've created? So that would mean delta G for the reaction is less than 0, whatever this composition is, which may not be K. Whereas if you're talking about delta G not being less than 0, then the reaction is only spontaneous at standard state conditions. So that's something you want to keep in mind, whether or not there's a not sign there, whether it's the standard state or the state that you're talking about. Okay. So on this page, they're just talking about Ks and what they mean. If K is more than 1, that means the products will be created. You'll get some products if your delta G is less than 0. So if delta G standard state is less than 0, that means K had to be greater than 1. So you can think about Ks and delta Gs in the same way when you think about whether or not something is thermodynamically feasible. Here it's saying if K is greater than 1, it's thermodynamically feasible. The reaction will go forward. And if it's not feasible. So if K is less than 1, that means delta G naught is positive. And then this book calls that being thermodynamically not feasible. And this is just what I wrote earlier, that you always want to interpret the significance of the standard states in terms of K and not in terms of whether or not the reaction at the conditions you created it is going to go forward or backwards. This table is probably a good thing just to look at. That'll help you think through some of the things that we've already learned, such as delta G is related to delta H. And so it includes in this little discussion, thermodynamic criteria of spontaneity, a discussion of the relationship between delta H and delta S. Okay, so I already derived this equation for you. Writing a reaction quotient, as you practice the problems, you'll remember that you put products over reactants, you put gases in pressure, you put solutions in molar concentration, and you leave liquids and solids out because their concentrations are essentially their density, which is constant. So if a reaction is at equilibrium, there we derive that equation. And then it's important to think about how you're going to get a delta G to get a K. So first, stop and do these two self-tests, because they just use some of the information we've already done. And then think about if you need a delta G to get a K, so if you need a delta G standard state, you can find delta G standard states of formation in the back of your book, and you do products minus reactants. So if you're at 25 degrees, it's okay to use this. But if you're not, then you'll have to calculate delta H with that same equation, getting delta H as a formation standard states, and delta S getting absolute entropies for the products minus reactants. And then you'd have to use those two in the delta G equation, because T is not 25, you'll have to put in whatever temperature you're at. So those are the two ways that you'd calculate a delta G, either directly from delta G's of formation if you're at 25, or by using delta H's and delta S's if you're not. Nothing new on that page. We've talked about everything there. And we've just talked about how you would calculate this from table values. And that is about it. You should read this last page because it gives some new definitions, endergonic and exergonic, and how they relate to whether or not K is greater than 1 or less than 1. So just read that last page. It's just two new words and to think about their definition. So that is it for the first topic in Focus 5.